Apologies there. Go back, share. So we're going to go to our virtual machine. Okay, start it up, and we're just going to start with the RSA algorithm that you guys have been working on for the homework. I think the last one, probably. And we're just going to create two prime numbers and try to encrypt. Okay. This is a much simpler problem, right? On the practical, I will actually hide a message. Like it'll be a quote from a movie, something like that. You have to tell me what movie that's from. This one is just the key part, basically. But make a note of how this works. Okay. All right. So we should have this. I'm gonna log in. All right, so let's open up a terminal. Do desktop. And then we're going to go into the CD/RSA code. Remember, that's what we've been using. If you're going to need both here, COI RSA and RSA full code. Okay, just keep that in mind. For this particular quiz that I've created for the actual practical, I'm going to change this obviously in a different way, but this illustrates your first example of how to do this. So I'm going to, I think I have. Yeah, sorry. I may have the numbers in here still, so I'm just I'm removing the numbers for the quiz. You know, let's get a glimpse of them. Okay. It's done. All right, so we should be good to go. All right, so I removed the old numbers. I'm just going to make up some new numbers, and then we'll go from here. So let's do the encryption again with, we would basically start here, right? So this, this algorithm, we've already discussed it in a previous lecture. So we can create two prime numbers. In this case, I'm just going to set two prime numbers randomly, and then we're going to print them out. Okay. And then we can compute n basically, which, as you know, is p times q. Then we're gonna run gen RSA. Gen RSA will give us our e and our d exponent, right? So as long as we have p and q, everything is good. So first I'm doing the process. I have my en, dn, print everything, print the public and private key. And really, the encryption even does not matter here. We're going to do the encryption and decryption on the other toy script, right? In this one, this is more about just getting the keys and breaking the key. Does that make sense? That's really, in the practical exam, I will probably use this also to encrypt the message. It's just I don't want to use a file here. Because if I use a file and everything, then it makes it harder for you to just write numbers. This is more of like a numbers quiz. So you'll just write down the numbers on a sheet of paper and put your name. All right, so let's go ahead and run it. That's basically what we should do. No, I didn't do any changes. So I'm going to run this as Python 3. Right, yeah. Sheet of paper. Okay, so it's taking some time there. I guess I'm using a big key for this one. Questions? All right, so it does that, right? So key things to look for in this script, what we want is the key. So this is really large. Okay. How about we try something small? Right, so what is the size of this key that I need? Input to the prime number must have been, yeah, okay, let's just use 256 for the seed size. More reasonable. Okay, I'm going to run it again. This will run faster. Okay, ran. Perfect. So now let's look at the, okay, something a little bit more reasonable. Right? The prime numbers are these, right? Very large prime number. You guys see that? Okay. I'm just going to go over the logic of this. The quiz is a slightly different, smaller numbers, obviously, because I don't expect you guys to write such a huge n, right? Okay, so P and Q there, then you get N. E we've established is usually 65,000. I'll talk a little bit about this after the quiz. If we have time, we'll go over that. Okay. So we have our E and our N. You can see that N starts here with 1666. And it ends with 2503. You can see that here as well. 2503166. So that's the public and the private key. Easy to detect the public key because it's got this 65537. And then the D exponent is this large thing, 12050 all the way to 7533. You guys see that? Okay, so that's basically the idea. So now what you would do is, well, you would have the public key. This is the n. That's the n that you have to factorize. Got it? And so how do you do that? You will go to FactorDB. So I'm going to open up here in the VM. FactorDB. So now the problem, factordb.com is literally like a website. So it's a database. You can look this up, but it may be too big. Okay, you can see it right there, factordb.com. Okay, so what you need to do in here is factorize. You just press the button, copy. Notice that this is a very long text box. I don't know if it's going to break, if it's going to factorize this, as it might be pretty large for it, but I can guarantee you it'll work for the problem I will give you. Okay. All right. So let's go ahead and try to copy this one. So you guys agree, right, that the number that I should factorize is this one, right? You all agree? Okay. So copy it. And it should give me these two prime numbers. Right. Oops. So then I'm going to paste this in here. Okay, see, that's a really large number. And you would hit factorize. And so these are the numbers, 1666. So I'm not really, it should be easier to read. So let's look at what we have in the code. One is a 4789, 347, and so I don't, it's not giving me information that I can use. Okay. So let's try just something smaller. Now, as I said, the numbers that I have picked are much smaller, so they will work fine. Okay, so let's try, give me two prime numbers. 57 is one, right? What's another one?
41.
41? Okay, you're certain those are prime numbers. So 57 times 41 is what? Who can do that on a calculator?
Two, 3, 3, 7. 2, 3, 3, 7.
2, 3, 3, 7. Okay. So this is a smaller number. So we're going to try it here in factor DB. I'm going to refresh. Go back. Refresh. Okay, remove. Okay. So it is expected, obviously, that factor DB can't factorize huge numbers, right? It's actually a good thing. You agree? Right. So, but let's do a smaller one. So 2, 3, 3, 7, right? So that may not have been prime. 57. 3 times 19 is what? So not prime. But you guys see the point, right? You guys get the point? All right, great. So so you would get just two numbers, the two primes, which are P and Q. Okay. So I think 11 is a prime. 11 times 41.
Four, 5, 1.
4, 5, 1. Thank you. Okay, so 4, 5, 1. $11 times 41. That's it, right? I mean, it's a no-brainer, but I have shown to you, right? So on the practical exam, I could go this route. I could go the quantum computer route. I mean, I'm showing you something. I could do both, right? If I just decide. It'll be some kind of a scavenger hunt. Okay, so now that we have these two numbers, what would you do? So let's say you factorized the n because you found it in the key. So then you would go into the code. So what do you need this code for? I'm going to clear. Okay, what do you need this code for? This code is basically to find D. That's really the thing that it's actually the only way that you will be able to find D. That I can tell you. I don't think I will create some other script or function to find D. So whenever you're looking for D, one thing you can kind of know as a rule is that you'll have to come here and figure out how to do that. So in my example, over here, I usually create the two prime numbers, P and Q. But actually, what you will need to do is, because you factorized it, you had the key, right? So you know, in some file you found the public key. I'll just do it as you found the public key to be E comma N. So that's in some file. I said it was the public key. You saw something in that format. Boom, that's your N. You put it on factor DB or something. Now it gave you P and Q. So instead of generating in this code for you to crack this, instead of generating the two prime numbers, just plug in the values that you just got from factor DB. You see what I'm saying? So here then you can just go here probably. And you would say P11, because that's what we found, right? 11 and 41, I think it was, for that 451, because we need two prime numbers. So, and then we have Q equal 41. This is important that you remember. Students struggle with this for some reason. They forget this one concept. Okay, once you do this, you have your P and Q. You know what E is because it's in here, right? It's in there also. And so what you're looking for is D, the private, right? And the private, basically, you know that it's two things. You don't know this one, but you do know this one because it's the same one. So all this code is to find this one over here. And okay, so how do you get that one? Well, when you run gen RSA here, notice that all you have to do is give it P and Q. And it gives you N, D, but it gives you the E basically. Does that make sense, guys? So that D, sorry, here is what you will have to find. Now you can obviously go into the code and change it to just give you D if you'd like. That's perfectly fine. But even as is, it should work. Now, at the heart of this, if you notice, is the logic of RSA, right? So you take P and Q, multiply it, get N. P minus 1, Q minus 1 gives you phi. And that phi is really important, as you can see, because to find D, you have to send phi in. You see that? You send E and phi in there so that it looks for specific Ds that meet specific conditions, as we have discussed in previous lectures. And then boom, you've got your D. Once you have your D, then you have your public and private key, and then you would proceed to decrypt. So for this code to work, I would have to give you a list of integers, remember? Or something in a specific format to fit in this code. But in this particular problem, I didn't do that. Instead, I'm just giving you a number. So you won't be able, this requires specific formatting to work. So on the practical, I will probably give you a file and it'll be in the right format. But here in this one, I'm not giving you. So the solution is that you will use the toy code because the toy code allows you to just process numbers, you know, and that's kind of how I've done the problem. All right, so now you have your D. That makes sense. So now that you have all the elements, you can go to the other code, ls-l, nano, toy, RSA, and if you, no, I deleted everything. All right, so in this toy RSA, oh yeah, here, see, these are the values. So in this toy RSA, what you need to do is, I will give you a cipher, right? That's the thing you're trying to break. That's like maybe someone's password to their cryptocurrency, right? You know that's how a lot of people, Satoshi, the guy who created Bitcoin, has over 1 million Bitcoin, worth about $1 trillion. And all that is needed to get that money out of there is like a key. It's like a code. And it's still sitting there, right? So that can be a lot of money. So that's how people do it. You know, I don't know if you ever heard the stories of people that used to mine like 7 years ago or 5 years ago. They left the keys in some hard drive. Maybe they were teenagers, then their mom threw the computer in the trash or something, and then they went to the dump to try to find it because it was worth millions of dollars. And some people found it, some people didn't. All right, so anyway, so what we're trying to get is the cipher here, and you will need to tell me what the message, the plain text was. So obviously, you just need to use decrypt RSA simple, plug in the cipher, plug in the N, which you have from the exam initially, but you don't have D. You have to compute. Got it? That's how you break RSA, and this will be kind of, this is just, I like to do this example so that you're a little bit prepared for the practical. In the practical, this would probably just give you a key, and then that key needs to be used to do a whole bunch of other decryptions, more on the block cipher symmetric approach. That's it. Any questions? Ready? Ready to have fun? All right, so I'm going to put up a whiteboard, and I'm just going to write the problem, and then obviously boot up your virtual machine. You'll have to use these codes, and please do not blare out the plain text message. I ask you that, you'll ruin the whole thing if you do that. Take out a sheet of paper, put your name on it, and then write down the answer. So you need to say M equal this number. Got it? Any questions? Perfect. All right, so let's go ahead and start the quiz. So I'm going to create a whiteboard for it. All right, so call this red. And this is break RSA, title of it. Okay, so I'm going to give you, so first of all, the public key, right? So the public key, pub. All right, so the EX, I'm not even going to say the letters or anything. You should be able to figure things out, right? So okay. Okay. This is 6. That's it. Good luck. And then the website, if you didn't catch that one, it was FactorDB for this exam. I'll pause the recording at this point. So we should be recording again. So we're going to go over the solution of this one. What was the answer? Matthew?
I think it was 651.
615.
Yeah.
615. So that,
I cleared my screen. I didn't write down on my computer, so
yeah.
I gave you.
No, that's great. So that was the answer, 615, right? So how do we get that 615? And so we're going to go over it. I have the quiz here, and then I'll do a second one, kind of to do a second example, and then we'll move on to some additional ideas. So I am sharing. Oh, I need to share, right? So I think I close it. Yeah. All right. Perfect. So we're going to share the screen. Right. Let me restart it, I guess. So once we go over the example, we'll talk about this, right? Like we'll talk about some of the, what you think about how RSA can be broken. Like, what are your thoughts on it? Okay. Okay, starting. And open up the terminal. I'm going to navigate to my scripts here. Okay, so the public key that I gave you, so you should know now, right? Public key look like that. This is kind of the format I will use. The 65537 should be familiar to you. That's kind of like a hint whenever you see that. And obviously the title will say public. So you have that. The value I gave you is 221.08307. All right, so you know that's the N. And we calculate N because it's P times Q. So we multiplied two prime numbers to obtain that. So you kind of know the hint here. Okay, if I want to break RSA, you look at something like this. You look at that number, you factorize it, right? So I'm going to go ahead and, we'll have a couple of alternatives going forward with the quantum computer. I'll do it maybe next week. I'll do an example with that. So you do 221.08307. So we factorize this one, and it gives us the two prime numbers, which are P5791 and Q38177. That's it. You've broken RSA. That's literally all you need. And that's like the hard part, right? So there may be other techniques, but this is certainly the most popular technique to break RSA. Okay, some website did it for you. All right, so now let's go ahead and, okay, so now that you have those, you know that I've mentioned that you really only have one script that I've given you. There's other libraries that you can use, of course, but you only have one script that I've given you that helps you to find the D exponent. If you get the D exponent for this, plus you have the N, you can do decryption. So now we're going to go into RSA full code. So I'm going to do nano RSA full code. And you can see that I have my function here. The gen RSA function will return the D that I'm looking for right there. So you can go here. Remember, I said you don't need to generate the P and Q because you already know what they are. So then you just plug in 5791 and then 38177. Do you guys see that? That's it. So then these two values that we got from the factorization will come here. One of these is your D exponent that you're looking for. Okay. So, and you'll have your E and everything. So let's go ahead and try that just to look at it. 3. Good. Okay, and there you go. So, I conveniently printed the keys here. So I know that's a public key. This is the private key. So boom. 4033793. That is your D exponent. That is what you needed to be able to perform the encryption. Now, I did say this would work if I had given you the data in the correct format, but I chose, kind of just wanted to do it with numbers, kind of like a, hand calculation problem. And so in future examples, if I give you and I say the data is here and you see it formatted like this, like a list of integers or something like that, you'll know that it'll probably fit in here. Does that make sense? But like I said, it's gonna be it's gonna be a whole lab session. So it's gonna be a Thursday. All lab will just be the practical. So there will be lots of steps, basically. Okay. And I'll provide hints along the way. All right. So now let's go ahead. So I have my D exponent. So I just, wrote it down on the quiz, 4033793. So then I want the M. I provided the C, right? So then you would go, once you have that value, you would go into the toy RSA example because that one has a very simple way of doing this calculation. So basically you can just go to the bottom here and you can see I even like hand coded these. So the cipher is provided in as part of the quiz, right? So you can just replace that. That was 32664,056. And then the N that was provided, that's that thing you broke, 221,08,3007. And then finally, the value that you broke is D, and that was 4033793. So now you're going to decrypt cipher, which will go in here into decrypted RSA, and the last thing it should print is the answer. I'm going to run that. I found 3, and it's taking a little bit. Did it take this long for you? Yeah.
Thought it wasn't working, so I cancel it.
You cancel, yeah. Yeah. So remember, as the things get bigger, it'll take even longer. All right, and there's the answer. The plain text is 6.5. So what do you think of this? It's amazing, right? That the whole internet, communications, etc., banking, Amazon, Brightspace, Zoom, everything works based on this, right? And based on this idea of asymmetric encryption. Now, this is the simplest implementation of RSA. There are additional things that you can do. For instance, making the message as big as the modulus. You know what I mean? Like you have the size of n, but this message is just smaller. Do you see that? And so people can do, how do you do that? How do you make the message be as big as n? Just pad it. So you can pad it, and then so there's additional things that people can do to improve security. It makes it harder to break. But those are more like technical things that have been implemented, right? Not really like the essence of the algorithm. The essence of the algorithm is this. Okay? So, but yeah, so that's basically the idea. So obviously, what is the recommendation here? You want this to be really big, right? So you saw it when I started the class, I tried my code actually uses big numbers, right? It starts at a seed of 256, and it is actually recommended nowadays to use like 4096 or something. Okay. We will do later on an example of performance where we will compare some block ciphers to RSA. RSA is significantly slower, as we have seen, and that's why I remind you, RSA is usually, or asymmetric encryption is only for the key, right? The secret, your secret AES or DES key is going to be encrypted with these procedures or these methods, and then the actual message, which might be a whole Netflix movie, you want to be able to encrypt that with something way faster, like XORing. And that's why XORing is really important, because you're just XORing bits, which is basically what circuits in a computer actually do. Got it, guys? Does this make sense? Are there any questions about this quiz? You now got to see the practical exam in a little bit more detail. Remember, I will use all the code that we've discussed this semester, including OpenSSL. So you need to practice those tools. If I use some code that's new, I will provide it. But otherwise, it'll be what's in my GitHub, basically, any one of those. Okay? Any questions? All right, great. So we did one example. I want to do one more like this. And then after that, we'll start talking about, okay, so we can encrypt a number. What if we want to start encrypting things like a word, right? So how do we go about that? And it'll just give us some interesting insights on things that we can do. All right, so there's a lot of very interesting things in this, right? So this is a problem that, basically you can find a lot of interesting things in just about anything if you study it for 20 years or 40 years, right? So these algorithms were started in the late 70s. Diffie-Hellman proposed the original asymmetric concept, but theirs didn't actually, although they proposed their idea, they didn't actually solve it, right? So it wasn't until RSA, Rivest and team, they came up with this algorithm which was adopted. All right, so let's say that I give you another. So we're just going to do this one really quick. I have another example here. I have a public key. Okay. Just to kind of bring this home, and the public key here is going to be 17. So this one's even simpler. 41,567. Okay, so that's my public key. And you also have a cipher. So you have a cipher that is cipher equal to 12992. Right? These are the values that I have there. Okay, so I'm just kind of saving them on the terminal. Now, what do I do? So I know 41,567 there is n. All right, so I'm going to proceed again to factor dB. So 41,567 factorize. Boom, 197 and 211. 197 and 211, those are my two prime numbers. So now I'm going to then proceed to my code. Right, so here this is terminal. I'm going to proceed to same example. Nano RSA, full code, right? So follow the procedure here. I'm gonna plug in those two prime numbers. One nine seven. Oops. 197. 211. That's basically it. And then gen RSA, my little function, right, takes P and Q and should return all the parameters. So let's go ahead and run it. So that didn't like them. It may be that they're just too small. Because it's an assertion error I got here.
I think it's a problem in Gen RSA because E for n less than like 65,000 something is supposed to be 3. But in this example, it's 17. So I think that's what's breaking.
Is it really? Okay.
Yeah.
Great catch. Thank you. I can see that now. All right. Perfect. So I have something hard coded in there. So if it's less than 65 and our E is what, 17? Yes, good catch. Good catch. All right, so let's try. So you saw, right? So that's good catch. Things need to match. If they don't match, it's not going to work, right? And so let's try it now. Clear. Hopefully it'll work. Yep, it worked. Nice. Thanks, Matthew. Nice catch. Yes, so that actually proved to us that, all these rules are, if we don't have the actual selection, like if we don't select the proper E and everything like that, it just won't work for it. Okay, so in this case, now we have the right terms and I'm able to get D. So what is D in this case? What's D? Yes, very good. 2663. So make a note of that. And now you can proceed to do the decryption, right? So that's what we're going to pursue. So I'm going to do clear here, /L. I'm going to go into my toy RSA. Okay, so I'm going to scroll down once again. I'm going to change these values. So D is 26633. My N is 41567. And then my cipher was 12992. Okay. $615, which I did start with 615 for both problems. Does that make sense, guys? Which one of the two approaches is more secure? The answer is neither. They're both easily breakable, but But if the bigger, the better, right? That's the key. Does that make sense? Are there any questions? Ready to move so we can move on from this? All right, perfect. So I think you guys understand. All right, so we looked at that. All right, so now we have about 20 minutes left or 18 minutes left. So in the last part of today, so I've been encrypting just a number, right? And then I also gave you code that can actually do a string. But how do we go about, let's say, kind of from scratch to encrypt the word RSA, for instance, or just some letters, A, B, C, D, E, F. So the key thing here is kind of the first thing I gave you at the beginning of the semester, which was the ASCII table. So we can always just resort back to the ASCII table, right? That, remember the letters have mappings to numbers, and then we can use that to perform our encryption. Okay, so I'm just going to do a simple example today of how, and again, the whole point of this exercise is just to show you some of the interesting things that happen with RSA. Okay, so we'll take a look at that. I do have, we're also going to look at things in a binary way, just for fun, just kind of observations more than anything, right, of how we can look at things. All right, so I'm going to start with, let's say, I'm gonna assume a problem where I have the public key and the private key already. So in this example, my public key is going to be, the E is going to be 79, the N is going to be 3337. Okay. And I can probably just do this on the whiteboard. The whiteboard here. We're not going to code this. I leave this as an exercise for you guys to do. You can do it in Python if you like. I'm just going to do it here. So, all right, let's look at an example of RSA. So we would, two large prime numbers, P and Q. Okay, P in this case is going to be 47. Q is going to be 70. Right, and then you know how to calculate things, so I'm just going to plug in the values themselves. So N here would be 3, 3, 3, 7. 5 is going to be 3, 2, 2, 0. Okay. So our E exponent is going to be 79. 9. Okay. And our D exponent should be 1019. 1019. So I'm not actually in this one calculating these or anything. We're just going to encrypt something that is a little bit longer than a number. So it's not just going to be like set, like a 65 or something like that. All right. So we have then our parameters here. We want to encrypt a message. So our message is going to be now, let's suppose that we want to encrypt the original message 688 23. So it's 688 232 687 687 966 688. Okay, so that's my message. So keep in mind, if it was letters, you could just convert them to the ASCII table equivalent, right? And then you'd have a sequence of numbers. The key here is going to be that we're going to need to break this into blocks, right? So that we do something consistently. So in my example here, let's suppose a block size of 3. Okay, so I'm going to suppose a block size equal to 3. All right. Okay. So now let's go to a new page here. Page. Okay. Whoops. Okay. All right. So now we're going to proceed to encrypt a message block by block, basically. Okay. So the blocks were, actually, I should write them down here. So blocks of 3. So it's going to be 6, 8, 8. Block of 3. 2, 3, 2. Block of 3. 6, 8, 7. Block of 3. 9, 6, 6. Block of 3. And finally, 6, 8, 8. Block of 3. All right. So we kind of established something like that. Remember, as I said, actually more secure implementations of RSAs create blocks of the input that gets padded if it doesn't have all the elements. And we know that the public key is going to be 79, comma 3337. Okay, so now we just proceed to do the encryption. So this is going to be, and pay attention to it. Let's see if you notice something, okay? Notice something interesting. So in this case, 688 to the what? To the 79, correct? Mod, I'll just use, well, I'll write mod. Mod, which is the percentage sign in Python. And then 3337. And that's going to be equal to 1570. Do you see that? Okay, that's the encrypted version of it. So you can corroborate this with the Python code. Then we're going to do the next one, the 232. So that's going to be 232, also 79, mod 3337, and that's going to be 2756. Okay. And then the next one, 687 to the 79, mod 3337, and that's going to be 2714. 714. Final two ones, 966 to the 79, mod 337 equal 2276. And finally, 688 to the 79, mod 3337, and that gives you 1570. Okay, so the encrypted message. So what do you notice? Doing cryptanalytics here. What pattern do you find in there? You should note that each block of 3 digits becomes a block of 4 digits. Do you notice that? We have 4, 4, 4, 4, 4, 4. All right, so pretty interesting, right? So how that works. Okay, so, and obviously to decrypt it, you would kind of do the thing in reverse. I won't do it for all of them, right? But now you would perform the decryption. So we'll just do it on the side for a couple of them. So you'd start with 15. So you guys tell me 1570. I guess we need to know the decryption exponent, which is 1000. So D is the private here is 1019 And then this is 3, 3, 3, 7. Okay. So now you proceed to take 1570 to the 1019 mod 3337, and that should give you 688. Does that make sense, guys? And this is how you can, if you'd like, you pretty much now at this point have everything that you want to create your own RSA from scratch. And you can take strings, right? So you would take a message in text, convert it into the equivalent ASCII value, ASCII number, etc. And boom, you can create a cipher. Got it? Does that make sense? So I wanted to show you that part because I know that's one thing that we've just been relying on the functions to do for us. But yeah, so that, I'll just do like ... here. So the last one would be it would be this one, right? So wait, notice there, yeah. So 157, 1570, 1570. 1019 mod 3337, and that should give you 688 again. Okay, so that's basically it. So some statistics here. The key size in RSA is normally selected by the user. 512 bits, which is one of the keys we've tried, is now no longer considered secure. Although it's still, in practice, it can still be difficult to break a message encrypted with a key that has a seed of 512 bits. Okay, so a 512-bit key. In practice, many implementations would choose something bigger, like 1024 bits. For more security, 2048 or even 4096 bits is recommended. I think in the code that I provided, 496 was at the high end there. With faster computers available today, the time taken to encrypt and decrypt a 496-bit modulus shouldn't be such an issue. And especially because you're just doing it for the key, so there might be a little bit of a delay there. Some additional statistics, block cipher algorithms such as DES or AES. So the RSA is, in theory, going to be 100 times slower than DES. 100 times slower, okay? So again, if you remember at the beginning of the semester, I said that when you're building SSL and things like that, performance is also important. Otherwise, if we were using, let's say, if we could use RSA to just do all encryption, well, that means that your movie would take, instead of a minute to download, about 100 minutes. So nobody wants to wait 100 minutes but that could be the world that we live in today, All right, so yeah, so there's basically that idea to be able to encrypt a message. So so basically I said in the previous example, right, I was trying to encrypt this message, which is this sequence of numbers, which I assume I could create a sequence of numbers like that by taking the letters and converting it into ASCII. We did the substitution cipher at the very beginning of the semester, where we actually kind of went through that whole process. And then here, I've shown you one very simplistic way of you using RSA to encrypt your own technique. All right. Yep. So I think that's it for I wanted to do the practical basically. We're done kind of with the theory of RSA, so hopefully that makes sense. I do have some slides and I will come back to them at some point, and then I'll check my notes to see if I missed anything. On Thursday, we're doing Pike Cryptodome. So if you remember, we started that last Tuesday but haven't finished it. There will be a demo type of a thing with Pike Cryptodome as well at some point. Okay. A homework where you have to really like use all those keys correctly. Got it? All right. So I'll see you guys on Thursday and for that lab.